In this video, I'm going to talk about a technique of integration. The technique is called integration by parts. I think that this is possibly the most important technique of integration, second only to U substitutions. In one of the past sections, we talked about how U substitution was the analog of chain rule. In this section, integration by parts is going to essentially be the analog of product rule for derivatives. So let's start by recalling what is product rule. So product rule is when I have the product of two functions. Usually we would call this f of x and g of x. I'm going to call it u of x and v of x. This is more standard notation for integration by parts. You'll see in a second. But if I have u of x times v of x and I want to take a derivative of this product, we would want it to just be the derivative of each of these factors, but that's not actually the case. By product rule, we see that it's the derivative of the first times the second factor plus the first factor times the derivative of the second factor. To relate this so this is an identity that we knew before from Calc 1. To relate this to integration, I'm going to take the integral of both sides of this. And just for notation's sake, instead of writing u of x and v of x, I'm just going to call them u and v, and we can sort of keep in our heads that it's actually u's and v's are names of functions like f and g. So I'm going to take the integral of this left-hand side, which is u times v prime, the derivative of u times v, with respect to x. And I'm also going to integrate this side, and to integrate it, I'm going to integrate term by term. So this is u prime times v dx plus the integral of u times v prime dx. The cool thing that happens, this side, the integral of a derivative by fundamental theorem of calculus, this is just sort of by inverse functions, we're undoing the integral of the derivative. This side becomes u times v, but this side still looks pretty messy, right? And I'm just going to rewrite it. We're going to do one last trick, and I'll show you why this trick becomes helpful in a second. I'm going to subtract this term from both sides, or move this term over, and I end up with u times v minus the integral of u prime times v dx is equal to the integral of u times v prime dx. And you say, why is that even something that's helpful? This, in a longhand notation, is a way of converting a product. Let's say that I started off with an integral that had a product in it. Here's a clever way to rewrite that integral product. And right now it doesn't look very clever, but I'll show you what it means in just a second. I'm going to write it one more time using the notation that I'll use through the rest of the video. The way that I'll write this is u times v minus the integral of v du because this is the derivative of u, v du, and I take that integral with respect to x, is equal to the integral of u dv times, or with respect to x. So this is my integration by parts rule. Let's see how it actually works out in practice. Here we have the integral of x times the cosine of x dx. On its own, it's hard to think how to solve this using a u substitution. Really, if you let u equal x, du is 1, it can't ever get rid of this x. It might be tempting to say, oh, the integral of this product would just be equal to the integral of each of the pieces, that I sort of want this to be 1/2 x squared, and the integral of cosine of x is sine of x plus c. But that's not the case. You can't integrate across a product, meaning that the integral of this product is not just the integral of each of these factors. So what are we going to do? we're going to use integration by parts. And looking at the rule that we had before, that we just found, I'm going to think of this integral as the integral of u dv dx. So I'm going to pick one of these factors to be a u, and I'm going to pick one of these factors to be a dv. And I'm going to be able to convert it into something that's going to be a little nicer. So how does that end up working out? The way that I'm going to do it in this example, let's set cosine x dx equal to dv. And let's set u equal to x. So this is my u, and then this is my dv dx piece. And in order to apply this rule, notice that I'm going to need some more information. I'm going to need to know what v is, and I'm also going to need to know what du is. So working from these pieces, if u is equal to x, then du is the derivative. So taking the derivative of u, I take the derivative of x, which is 1 dx. Over on this side, so that's the derivative. On this side, I'm going to take the antiderivative, because I already have the derivative over here. I already have this in terms of dv, so I want to take the antiderivative to find out what v is going to be equal to. The antiderivative of cosine is sine, and we have each of the pieces that we need in order to be able to do our use substitution. Let's remind ourselves of the rule. The rule is that well, maybe I have it written in the backwards order over here, but I'll have it written as the integral of u dv dx is equal to u times v minus the integral of v du dx. So let's put all these pieces together. I started with the integral of u dv, because that's how I set this up. And now I'm going to need to know what are the other pieces. In this case, u times v is going to be x times sine of x. And maybe I could use arrows, maybe that would make it more confusing. In this case, it means that my original integral, the integral of x times cosine x dx, is equal to the integral of u times v, which in this case is x times sine of x, minus the integral of v du. V is sine of x, and du in this case is just 1. Great. So now my original integral is actually equal to this much more simple integral. It's equal to x times sine of x minus the integral of sine of x dx. So notice the integration of parts took this really messy product and it turned it into some numbers minus this thing that was easy to integrate, that I know how to integrate the sine of x. The sine of x is actually cosine of x. So my final answer is going to be x sine of x minus the integral of sine is cosine. No, the derivative of sine is cosine. The integral of sine is negative cosine plus c, which ends up being x sine of x plus cosine of x plus c. In the remainder of the video, I'm going to do a number of frequent examples so that we get the hang of where the u's and v's go and how to select which piece from which. So let's look at another example. I have x times the natural log of x dx, and I need to decide which piece is going to be my u piece and which piece is going to be my dv piece. So the hardest part of integration by parts is figuring out which part is which. And you sort of have to think through logically which place could go where. In this case, natural log of x is a good candidate for u because, let me focus this again, it looks unfocused. Sorry, Because we know what the derivative of natural log of x is. The derivative of natural log of x is 1 over x. We actually don't know what the integral of natural log of x is yet. That's something that we're going to look at in maybe the next couple of examples from here. So one way to decide which piece to go where is to figure out, well, which piece can I take an integral of, an antiderivative of? Another thing to consider, sometimes it is nice to put x as u because I know that the derivative of x is just 1 and it can just disappear. So if I have an option to put an x as u, I'll try to take it. In this case, I don't have the option, that I need to put natural log of x in for u because, whoops, because I shouldn't have included this whole thing. It's just natural log of x is in for u. Because I don't know what the antiderivative of natural log of x is. So if natural log of x is u, that means x has to be dv. I take the derivative of u, the derivative of natural log is 1 over x dx. The antiderivative of x is 1/2 x squared. Again, I'm taking the derivative here and I'm taking the antiderivative here. And now I have all of the pieces to be able to do integration by parts. The song that I sing in my head is that the integral of u dv is equal to uv, which is natural log of x times 1/2 x squared, minus the integral of v du. So I'm taking this v piece and I'm taking this du piece, and that's what gets put into this integral. So that's 1/2 x squared times 1 over x dx. This front part has already been integrated. There's nothing that needs to be done. That these are just function pieces that I'm going to leave here. My integral, it looks like something nice can happen. I have my 1/2 coefficient that I take out front of the integral, and I have x squared times x leaves me with just an x in the integral. And again, these are nice examples that I'm using. Integration by parts gives us a much nicer integral to deal with than the original integral that we were looking at. Now I just have to take the integral of x, which I know is 1/2 x squared plus c. And my final answer ends up being 1/2 the natural log of x times x squared minus 1/4 x squared plus c. What happens if I have bounds on the integral? This is something that comes up. This is a tricky example for two reasons, but we're gonna, one, it's a bounded integral, and two, let's go through the process. I'm not gonna use colors because we're experts at colors. Where do I want my u and where do I want my dv? In this case, I'm gonna set u equal to x squared and I'm gonna set dv equal to e to the x, because I know that the antiderivative of e to the x is just e to the x. So over here, this stays nice, sort of. The antiderivatives of e to the x remain the same. Whereas over on this side, taking my derivative, my x squared reduces by a power, so it gets a little bit more simple. That's my rationale behind choosing the way that I choose. If you flip-flopped and did it the other way, you might do a couple of iterations and see if it works out or see if it doesn't. But we haven't quite finished solving the integral, right? So my integral, the integral from 0 to 1 of x squared e to the x dx, so this was u dv is equal to uv x squared times e to the x minus the integral of v du, which is e to the x times 2x dx. So this did get simpler, but I still can't quite integrate this one. This is a case where I'm going to have to do integration by parts twice. I did it once, and I reduced the power of the x a little bit, but I'm going to have to do it a second time and reduce the power on the x even more. So let's do some more scratch work. I'm going to set my u equal to 2x, my du is equal to 2 dx, dv is equal to e to the x, and v, the antiderivative of e to the x, is still just e to the x. So now I'm prepared to do integration by parts a second time. So rewriting, we still have this out front. We still have the x squared times e to the x out front. And now we're subtracting this whole thing, uv minus the integral of v du. So what's uv is 2x e to the x minus the integral of v du, which in this case is a nice thing to integrate. 2 e to the x dx. So we did integration by parts once, it got a little simpler. We did integration by parts again, it got even more simple. Now, notice this is no longer within the integral sign, this is just a function out front. So I end up with x squared times e to the x minus 2x e to the x minus the integral of 2 times e to the x is just 2 e to the x plus c. Oh, but wait. Notice this was an example where I had definite bounds. So throughout this entire example, I need to make sure that I keep track of my bounds. For me personally, sometimes you can look and do it at the very end, that these integrals should be going from 0 to 1. But also, these functions need to be evaluated from 0 to 1. When I did this integration by parts and got u times v is also evaluated from 0 to 1 and from 0 to 1. And so this entire expression, I'm actually going to write it evaluated as x goes from 0 to x goes to 1. So it means I need to plug in 1 for each of my x's, and then I subtract off where x equals 0 in each of my x's. And what do I get? I get 1 squared times e to the 1 minus 2 times 1 times e to the 1 minus 2 times e to the 1 plus c. And of course the c's are going to cancel out because it's a definite integral. And then I'm going to subtract out when I plug in 0. In this case I need to go through the work of plugging in 0 because notice that e to the 0 is not 0, e to the 0 is 1. So I plug in 0. This first term I get 0 times something is 0, minus 2 times 0 is 0, minus 2 times e to the 0, which is just 1, plus c. And my final answer, combining all of these terms, I get e minus 2e minus 2 more e's is e minus 4 e's, which is minus 3e, minus a negative 2 is plus 2. So the thing to remember when evaluating bounds, you need to make sure that you evaluate it for every single piece, every single part of the integration by parts. Maybe I'll even write that down. Evaluate bounds on every part of the integration by parts. Now we're going to get into some trickier examples. The last two examples I want to show you are tricky examples using integration by parts. Here's something that doesn't look like a product, right? That I don't have the natural log times something. So we're going to add in the trickiest part there is. And as we talked before, we know what the derivative of natural log of x is, but we don't know what the antiderivative is yet. And that's what this is asking. What is the antiderivative of natural log of x? How do we solve this? We're going to set it up doing integration by parts. I need to pick out my u and I need to pick out my dv. Like we just said, we know what the derivative of natural log is, so that's a good candidate for our u. And I'm going to be clever. I'll pencil this in. Right? So here's my clever thing, that the natural log of x is still the same as the natural log of x times 1. So I let my dv be equal to 1. There's always a hidden coefficient of 1 within any sort of function. And what does that do for us? Well, it means that, one, I probably wouldn't have thought of this. If this wasn't a problem on integration by parts, then it's hard to know to sneak in that clever version of 1. But if I were to tell you to use 1 as one of the parts in the integration by parts, now you know how to do it. Also, it gives us a result that's an important result, that the derivative of u, the derivative of natural log, is 1 over x dx, and the antiderivative of 1 gives us v, which is x. So, by integration of parts, the integral of the natural log of x times 1 dx is uv minus the integral of v du. So what is that? uv is x, well, maybe I should have written in the right order. uv is natural log of x times x, and be careful, that's not an x squared. This x is in this natural log function. Natural log of x times x minus the integral of v du, which, look at how cool this works out. The integral of v du is x times 1 over x, and we end up with, usually we write it in the order x times natural log of x. That way there isn't confusion that you think that the x should be squared. Minus the integral of x times 1 over x is just 1. What's the integral of 1? The antiderivative of 1. You can use power rule. You can think of this as x to the 0. It gets raised up and becomes x plus c. And that's our answer, that the integral of natural log of x is x ln x minus x plus c. For this last example, I'm going to call it going in circles, and you'll see why in just a second. That I can see that this is a product, and so it's nice to do integration by parts. I'm going to set u equal to sine of x, and du, and then dv, the other piece, becomes e to the x dx. Why did I do that? This isn't actually an example where you could have chosen it to go either way. I just like having e to the x as the dv because then my antiderivative is really easy. The derivative of sine of x is also easy. It's the cosine of x. So now I know that this integral, the integral of e to the x sine of x dx, is going to be equal to uv minus the integral of v du, and that becomes sine of x e to the x minus the integral of e to the x times cosine x dx. I forgot my dx. Well, it looks like we haven't gotten this much simpler, because e to the x sine x, pretty similar to e to the x times cosine x. This just means that we're going to have to do it again, and this is us going in circles. I'm going to do integration by parts a second time with a similar sort of a setup. I'm going to let my u equal cosine x, and I'm letting my dv be e to the x dx because I want to do an easy antiderivative. I don't like antiderivatives as much as I like derivatives. So my easy antiderivative is e to the x. The derivative of this, the derivative of cosine, becomes negative sine of x dx. So this whole integral here becomes the pieces integration by parts. So I get sine of x e to the x minus, notice that I take this along. Sometimes it's easy to forget it if you just like leave it out somewhere. So be conscientious of all of the different functions that get left behind when doing integration by parts multiple times. So this integral, by integration by parts, it's uv minus the integral of v du. U times v is cosine x e to the x minus the integral of v du becomes the integral of e to the x times negative sine of x dx. And I'll simplify this algebraically a little bit. So this is minus cosine x e to the x. This is a negative sign, and a negative integral becomes positive, but then I'm subtracting this whole thing so it becomes negative again. So positive, negative, minus the integral of e to the x sine x dx. Wait a second. We just did integration by parts twice, and we got back to an integral that was what we started. How is this even a possible successful method for doing integration by parts, right? Because what we want to do is we want to find what is the integral of e to the x sine x, and we got that it's this messy stuff minus the integral back again. We're going to do some clever algebra here. Notice that because the original integral is exactly equal to this integral, I can add to both sides of the equals sign this integral, right? This is algebra, that if I have, I'm just going to like add positive a to both sides of an equation when solving. I add to this side and I add to this side. These cancel and become 0, and this becomes 2 copies of the integral of e to the x sine x dx, right? Because I have not 1 but 2 when I added this integral of e to the x sine x to both sides. That's equal to sine of x e to the x minus the cosine of x e to the x. Does that algebra make sense? So I had this long equation that I got from integration by parts twice, and I notice that I have the same factor in common on both sides, or the same term in common on both sides. So I add that. I get 2 of them on this side they cancel out, and really we're done. We don't have to do any actual integration in this problem, because now this is exactly what we were looking for. If I divide both sides by 2, it's too bad there's not enough room on this page, but I'm going to divide both sides by 2, and I get the integral of e to the x sine of x dx is equal to 1/2 of sine x e to the x minus cosine x e to the x. And that's exactly what we were looking for. That's exactly what our original problem was asking. It's asking, what is this integral? Oh, I found out exactly what it is. Oh, but I do need to add in my constant of integration that is easily forgotten in these cases when I don't actually take the antiderivative, but we do want the general antiderivative, so, whoops, sorry, we do want the general antiderivative, so we need to add the plus c.